All right, 12 o'clock on the dot. We will get started. I'm so excited that you have joined us again for episode 2 of our Irrigation Excellence program. We had last week, or I guess 2 weeks ago, we met and did the same type of discussion on crop water use, and that is posted on the Keys to Agronomy YouTube page. I can send you a link. If you have not received that link, please let me know. That way you are able to view this content. We do want to thank Dr. Dana Porter, who is with us, sharing her knowledge from these years that she has been in. We call it seasoned. So we are excited that she is sharing her knowledge with us. I'm looking forward to a great visit today. We do want this to be super informal, so if you have questions, please feel free to raise your hand, put them in the chat, or just unmute yourself and feel free to ask them as we continue through this program. Again, we want it to be very informal, and we want you to be sure that you are learning what you need to be learning and the expectations that you are getting while you're here. Again, my name is Christy Keys. I'm the agronomy agent for Castro, Hill, and Lamb County up in the Texas Panhandle. I know we have lots of people from around Texas that are joining us on this webinar, and we cannot thank you enough. I'm going to turn it over to Dr. Dana Porter.
Thank you, Christy. Appreciate you very much. Welcome back for those who come back, or welcome if this is your first time. We really appreciate the opportunity to visit with you, get some communication started and conversations about soils today. Again, just a little background. Christy, you met. She's our extension agent agronomy, Texas A&M AgriLife Extension Service in Hale, Castro, and Lamb counties. And I am Dana Porter, extension program leader and extension specialist, biological and agricultural engineering. Trying to get my little thing worked out. Just a quick acknowledgement. For those who pay the bills, we really appreciate the support from USDA ARS Ogallala Aquifer Program, the USDA NIFA Hatch Project, and the High Plains Underground Water Conservation District. Just a quick recap in case some of you weren't here last time. Water issues consistently rank among the top extension program needs statewide. So that is why Christy and I are focusing on water issues, plus it's our job. So we're going to do that. We're glad that you're here. This water management series will be addressing various water resources, information resources, technologies, and so on. So we're going to include this webinar series. A little later after planting, we're going to have some more webinars, some in-person workshops, and field days. So be watching Christy's communications for these. Some of the topics that we're covering, fundamentals, and we're going to continue those today with soil water principles, and you can see some of the upcoming topics. If there's something else that you're interested in, we welcome your input and feedback there. Again, some interactive workshops a little later on that we can focus on operation and field specific considerations, as well as some technical tours, and get out in the field and do some show and tell. So for this second session, we're going to be talking about understanding and managing soil water. So did a lot of my graduate work, and ever since then, a long time ago, as contrary to popular belief, I wasn't here when God created soil, but I came here shortly after. So let's just back up. Let's just kind of review really quickly. We talked briefly about soil water plant relationships last time. We focused on transpiration and evaporation, basically the plant side of things last time. This time we're going to dig into the soil a little more assertively here. So we have our evaporation from wet surfaces. We talked about the transpiration, and then let's dig into the other. Trying to get through this just a minute. Sorry. I was going to do a quick recap of evapotranspiration. So we had evaporation from the soil surfaces, wet soil, wet leaves, standing water, transpiration, of course, through the plant. Atmospheric pressure, atmospheric conditions. We talked about, a hot, dry, windy day, we're going to use more water than on a cool, rainy day. Plant factors, we talked about the plant type and the growth stage, canopy cover, and those sorts of things that affect soil water. So now we're going to focus on the soil factors. We can't evaporate water that's not in the soil. So, or we have to have the soil moisture to have something for the crop to use. So we're going to be talking about that. Back up again on this just general long-term average crop water demand for cotton. We remember that the emergence, when we first get the cotyledon stage, when the plant first emerges, it doesn't use much water, but we watch as the vegetative development continues, the water increases. We also noted certain stages of the crop and the approximate water use. And then we landed at relating that irrigation system capacity to depth of application. And so if we back up here to the cotton, to get full crop water demand at peak bloom, about a third of an inch a day, we would need 6 gallons per minute per acre. So most of us don't have 6 gallons per minute per acre to use. So now that's where we're going to start talking about soil water and managing that so that we can minimize crop loss due to drought stress. Some effective root zone depths reported for agronomic crops. This is from a variety of sources I looked at from across the U.S. Alfalfa, we know you can put some deep roots with alfalfa, especially if you have a deep soil. Corn, cotton, sorghum, generally 3 to 6 feet is about as deep as you're going to have effective roots. Peanuts, a little shallower. Our vegetable crops are shallower. And what we know too is, from years of experience, most of the water we're using or the plant is going to extract is from the top 1 to 3 feet of soil. And that is if there's moisture there and if there are roots there. The irrigation management and timing is going to be more critical for shallow-rooted crops and for shallow-rooted crops and for drought-sensitive crops. So we also remember that nutrients are taken up with water. And so in micro irrigation systems, the effective wetted zone may be substantially reduced. Again, that comes with management, and we're going to talk a little bit about how we encourage a deep and wide root system. What a plant wants, it needs sufficient soil moisture to prevent drought stress, but not so much that it's waterlogged. The plant roots need water and oxygen, so we're going to try to manage that. Roots grow in moist soil. They don't go hunting for moisture and nutrients. So we're going to encourage that deep, moist root zone if we can. Whoops, sorry. I'm jumping with my mouse, sorry. So this general root zone that we have here, trying to relay that most of the water is going to be taken up from the shallow soil moisture first, if I have roots there, and then later in the season, if roots are available and if the water is available, I start to pull water from deeper in the root zone. If I have a confining layer, like a caliche layer, or a really dry layer, compacted plow pan, waterlogging, or it could be a salt layer, I can limit effective root zone development at that point. And so I'm going to have a much smaller root zone to manage. That's going to make it a lot more tricky. So let's dig into the soil moisture. And any questions, please feel free to jump in. Any corrections too. I know there's some folks that work a lot with soils on this call. So let's go. Going back to this, we have our infiltration and runoff. We're going to be talking about those. The rate of infiltration and runoff depends on water depends on how fast the soil can take in the water. So we're going to be looking really more in depth with these. In some circumstances, we're going to need to leach salts from deep from below the root zone. So we want to try to flush those salts out sometimes. We're going to get into that in a future session. But really, when we're looking at managing our water, we want to reduce deep percolation losses below the root zone, and we want to reduce evaporation, and we want to reduce runoff where we can. So let's look more closely at these components: infiltration, runoff, and deep percolation. And when I do that, I'm looking at rainfall that falls at a high rate of intensity, or irrigation that is applied at a high rate. If we exceed the soil's infiltration capacity, also known as permeability, the water will pond or run off, or sometimes both. The water applied in excess of the soil's water holding capacity will drain unless there's an impeding layer. So we look at our what those factors are that affect soil runoff. Slope and and surface storage are keys. So you've seen furrow dikes. That's the image that's in that photo there. Basically, it's really intuitive. Steeper slopes, you're more likely to have runoff. If I have a more intense rainfall or higher irrigation rates, I'm more likely to have runoff. And these can go into decisions with nozzle packages and irrigation management. So we want to try to reduce that runoff potential, adjusting nozzle packages and also adjusting the nozzle, the speed of the pivot. That's how we're going to reduce runoff. Surface storage, again, we can increase that with the furrow dikes, crop residues, contour tillage. The idea there is to hold the water in place or reduce the effective slope so the water can infiltrate the soil. We want to hold it on the soil so that it can go ahead and soak in. Permeability is affected by the soil texture and structure, as well as soil moisture. So coarse textured soils, again, pretty intuitive if you've been out in the field. Coarse textured soils like sands have a higher permeability than finer textured soils like your clay loams or your clays. Soils with stable aggregates generally also have a higher permeability than soils without good aggregation. So there's some benefits of soil organic matter, mulches, long chain polyacrylamides or PAM, some of those additions. That's what they're trying to do, is maintain the aggregates to maintain the permeability. Dry soils generally have a higher permeability than wet soils, especially if we're talking about swelling clays. A few of you may have swelling clays in your soils. I grabbed these numbers from the USDA NRCS web soil survey. We're going to get into that a little bit more later, but I can just look at some comparisons for some of the soils in the Texas High Plains and South Plains. Generally, these web soil surveys are going to give us depths of our horizon, of our layers, the textures that are in the different layers, permeability or the infiltration. Whoops, sorry. Infiltration rate is permeability in inches per hour or centimeters per hour, and available water holding, which inches of water per inches of soil. So you look at that as a 14 to 17% of the volume can be held as water in that ACUF top layer, for instance. So we're going to be looking more in depth at this. So if I want to look at the that components and the water holding of our soils, it's going to look something like this. Whoops, I'm going to go back. I'm going to dig into that further. But if I have a really, really wet soil at saturation, if I let that soil drain, let the initial water drain, that's going to be filled capacity. The water that's drained away is gravimetric water. Between filled capacity, what that soil can hold against gravity, and a point we call permanent wilting point, when the plant can no longer take in the water, that's our plant available water, and that's what we're measuring. Our soils don't become totally dry unless we oven dry them. The water that's held really tightly to the soil particles is what we call hygroscopic water. Not a name you're going to use a lot, but just so that you know that dry soil is not really, really dry. There's some moisture in there, but the plant just can't take it. Now we look at the relative water holding, capacity, or what we call plant available water, is that for these different soils, generally with a fine sandy soil, you'll see about a little over half an inch to a little over an inch of water storage per foot of soil depth. Your loamy soils and your clay soils hold more water. So that's this image tries to portray that. Come back and I'll look at that again, back to that far right column. That's going to give the general ratios. If I want to, oops, sorry. If I expand a little bit and I want to calculate how much water holding capacity in root zone depth, 1 foot to 5 feet, I calculated here, you can see approximately how much water that I'm holding. So if I'm managing a 3-foot depth root zone in an Amarillo fine sandy loam, I've got about 5.5 inches water holding capacity in that top 3 feet of soil. So that's the water that I'm going to be managing. This becomes important when I start talking about soil water monitoring. Is sometimes you may see some reports of some fairly wild claims about water availability. It's important to understand what the soil really will hold when you start evaluating technologies and evaluating research studies evaluating advertising claims of what significance these really can have. So again, looking at that saturated, the gravimetric water, draining out, I get to field capacity, and then my plant can absorb water, take up water through transpiration. I have evaporation going on all the time. I still have gravity working on my soil water too. And I get down to permanent wilting point, beyond which my plant really can't effectively recover if I dry out that much overnight. Okay, and back to that same, and I welcome questions on this, and we'll go, I keep showing this a lot, but I really want you to understand how much a realistic water holding capacity is when we start getting into a little bit further and what we're actually managing. So I look at the soil moisture characteristic curves. Basically, these are general depictions of what the relationships between what soil water content and soil water potential. So as the soil, if I have an initially really wet soil, my water holding capacity, my sand will hold less than a finer soil. But I look as the soil water suction increases, the plant available water for the sand really drops off quickly and kind of stabilizes to a permanent wilting point fairly quickly. That finer soils tend to hold the water more tightly and they're a little more forgiving, I guess, for management. When we look at for irrigation standpoint, they're a little more forgiving. So a lot of our research studies have been done at Halfway, Bushland, Texas, Garden City, Kansas. These are mostly Pullman clay loam, Olton clay loam soils. So when you're reading and interpreting research studies, this is important. What soil did they do it on, and how forgiving, if you will, is that soil? Another topic that we use, or concept that we use, is management allowable depletion, or MAD. We don't want, if we go back up here, we don't want the soil to get so dry that the plant is going to be stressed. So we kind of grab a management allowable depletion. It is not scientific. It's from years of experience and research. A lot of our agronomic crops, drought tolerant crops, we use typically 50 to 60% management allowable depletion. For more drought sensitive crops, like your vegetable crops, we don't want to dry it down that much. 25 to 30% management allowable depletion is more reasonable for those crops. In other words, we just don't want to dry the soil down so much that we're going to stress the crop too much. So what does that mean? If I take those same soils, come back, and my plant available water I calculated, look again at the Amarillo fine sandy loam at for a 3-foot depth, I can hold 5.5 inches of plant available water, but my management allowable depletion is 2.7 inches. And so that's what I'm really managing in irrigation, or that's what I'm really trying to achieve with my irrigation. I don't want to use more than that 2.7 inches before I come back and refill that plant field capacity again. Otherwise, I'm starting to look at plant stresses. And if you do any soil moisture monitoring, you're probably already familiar with this. Again, here's just some other crops for the same soils for 25% management allowable depletion. So really, I'm only managing an inch or an inch and a half of water at that standpoint for those more sensitive crops. Okay, so where I'm getting all these numbers is from the USDA NRCS Web Soil Survey. And here's the website. You click on the green button. And Christy and I have talked about having some workshops if you want to sit down and look more closely at your specific soils, at your specific fields. We can do that, look at the water holding capacity and that sort of information. That's better and more easily done in a small group context, so we can sit down one-on-one with you. But if I clicked on that green button, I can look at this web soil survey, I can locate my field, zoom in the map. It's kind of like using Google Maps. I can zoom right on down, get to my field, create an area of interest, create a soil map, and then I find out information about those specific soils. So So that's how that's going to work. And like I said, we'll dig through this more slowly and more operation and field specific with you at your request, at your leisure. We'll do that. The way it looks when I pull up the soil physical properties, it is going to provide the soil name, the depths of each layer, the percent sand silt clay and bulk densities, saturated hydraulic conductivity, that is that infiltration capacity I talked about, and the available water capacity, that's the stored water or inches per inch of water. So inches water per inch of soil storage. So for that bovina soil, the top layer, it's look at 12 to 18% soil moisture is the field capacity. And I've also got some information about soil organic matter and some other things in those. And these can change a little bit from county to county. So when I zoom in, if I have a Pullman clay loam soil at halfway, then the values might be a little different than they would be in Carson County, mainly because the soil layer depths are different. So I come back and take another look at that. Again, that's where I got that information, and I just throw them into this handy dandy table for my convenience. And I've made these presentations before, so you can see how much water holding capacity. Again, you can compare the Amarillo and sandy loam to the Pullman clay loam, and they're a little bit different. Now we start looking at some textural classes and the effects of soil organic matter. You hear a lot about soil health and soil organic matter and the value of that. I've got this reference that I think is helpful. USDA NRCS did a pretty decent literature review looking at research studies over time, looking at the effects of increasing soil organic matter on available water content and on water retention. And basically, just grabbing for a brownfield sand to take a sandy soil, if we increased available water holding capacity from 0.1 centimeter per centimeter to 1.22 centimeters per centimeter, the water holding capacity for a 3-foot root zone increases from 3.6 inches to 4.3 inches. Okay, for a Pullman clay loam, you're looking at increasing from about 5.7 inches to about 6.7 inches in a 3-foot root zone. And that's to be optimistic if we're really able to increase our organic matter substantially. By comparison, a muck soil can hold approximately 40% available water content, or 14 inches in a 3-foot root zone. Why do I say that? Because I've heard people claim they can get 14 inches of plant available water in an acre of soil in the Texas High Plains. Well, that's really probably not reasonable. So I need to ask the question, what is a reasonable improvement? And just kind of look at that to evaluate those studies. For instance, a muck soil, we don't have these. I had to go up to the Midwest to find one on a soil map. And so just to get an idea. So again, available water holding content, plant available water is not going to increase that much. Now, water retention is another animal. It's how much water can I get into the soil. That can definitely be improved with organic matter. Our aggregate retention or aggregate stabilities can increase with soil organic matter. So just wanted you to understand there's a difference there. So when you're reading these studies, reading the brochures, just so you can to ask the right questions, basically. Estimating soil moisture, there's a lot of ways we can do, a lot of tools. There are a variety of sensors commercially available now. Each has its advantages and limitations. The data services and packaging, there's a lot of data packaging. This has helped us a lot in adoption of soil moisture monitoring, because in the old days, we had to hook up our little handy dandy meter and into each sensor. That's really inconvenient, especially later in the season. But now with the telemetry systems, the gateways, data gateways, we can do a lot to simplify and make those data collections a lot more simple, a lot easier, a lot faster. So anyway, there have been a lot of improvements, mainly in the way the data are collected and packaged. Some of the technologies are not that new, but but definitely the devices have improved. Some issues that we want to look at, though, are applicability and limitations. Not all sensors are created equal. For instance, I wouldn't use a tensiometer in a cotton field. It's too sensitive to a drop in water. That's more useful in, for instance, a horticultural crop or a nursery crop. Siting and installation are important. I'm going to show some slides on that in a minute. Calibration is important. Education and tech support. If I have a sensor, but if I have a problem with it and I don't have anybody to call to ask my questions, that makes it less useful to me. It makes it more challenging to learn. So there's just a lot of considerations in choosing which sensor, and of course, cost and cost share opportunities. And do I own the sensor, or am I leasing the sensor, for instance? Those are all considerations that you might want to take into account. The most portable device that I've used is the estimating soil moisture by feel and appearance. Probably if you took a soil science class in college, you did this. Maybe in FFA soil competition, you did this. And there's a really good publication from USDA NRCS that describes how to do that. Basically, if I take a soil sample, squeeze it, and water squishes out, it's wet. And if it blows away in my hand, it's dry. But there's some really good guidelines here that will help you. Some sensors that we've just got a lot of. These are just some examples of some of the sensors that we've studied in the field. There was some questions that came up several years ago about what sensors we would recommend, and does it matter how I install them? So USDA NRCS Conservation Innovation Grant that we addressed with, really the leader of this was Soleil Tagvian out of Oklahoma State University, Jonathan Aguilar out of Kansas State University, and then this team from Texas. And we looked at a bunch of different sensors. What we wanted to do is look at sensor accuracy. How good is their calibration right out of the box? Sensor prices, sensor reliability and durability, quality, and so on. So we kind of looked at these. Again, here are the sensors that we chose for the study initially. Over time, we added more sensors because since we had these in the field long term, a lot of people wanted to jump on the bandwagon. So here's where we did. We did the work at Bushland, Texas, at the Emily Field. That's an AgriLife Research managed Emily Field. It's in Bushland. To the right of that picture is Bushland Elementary. Across that's Interstate 40. So that tells you exactly where that is. We had the test under 3 different irrigation scenarios. The 50% ET was a dryer treatment. 75% ET was what most of us manage at. And then we had 100% ET replacement. This was under corn, just for a wet treatment. We had a bunch of sensors. It was a mess in the lab, but we hooked them all up, made sure they were all connected and working and programmed, stuck them in the field, and then shoved all those wires in a box for our data logger. That's Thomas Marek doing the work out in the field. In the picture, we have Jed Moorhead. You can't see him. He's hidden in the back. Standing is in the front here is Gary Marek and Kevin Heflin, a familiar face for some of you, in the checked shirt there. So we had a lot of really great help. Got the data during the season. It looked something like this. You can barely see where our sensors were, but we published some data, and this is published in Sensors Journal. I've included the address here, and it's also later in the presentation, but I looked at inserting the different sensors. We looked at inserting the different sensors vertically. The vertical insertion would be like normal people would do, where you drill a hole and put the sensor in vertically. The horizontal insertion would be a lot of recommendations for some researchers say dig a trench and then insert the sensor in horizontally in undisturbed soil to ensure good contact. And then the laid horizontal, the middle column we said, what happens if we trench it, lay those suckers in, and then cover it back up? How long does it take to stabilize? But what we can see from this image is that all of them responded to the changes in soil water. We compared them with a calibrated neutron probe readings. So we could see how they compared to that, how accurate they were, how close they were. If I look at the black line, that's the trend line, black solid line compared to the dotted reddish orange line, which is a 45-degree angle there. That's this looking at how close we were to the actual soil moisture line. The watermarks tended to, on the bottom there, they tended to under represent the soil water, but the calibration is pretty much, the slope is pretty similar to that orange line. So it was really good, easy to calibrate. It didn't, the watermarks didn't care if we laid them in horizontally or vertically. They're pretty small sensor anyway. They didn't really care vertically or horizontally. The other sensors did care. The slopes of those black lines are different depending on how we inserted them. And these were replicated. We have multiple sensors, at least 3 sensors at each depth in each irrigation treatment. So we had a whole lot of data coming in. But I think this is kind of interesting. The calibrations also would not be completely linear for some of these. But I think this is really good work. I appreciate Doctors Heflin, Marek, and Marek doing this work. Again, a little closer look at the decagon sensor and the watermark sensor just for grins here. And you can see what that slope looked like. The decagon horizontal insertion was pretty close to the vertical insertion, really close to accurate. So you can see that. So the results were the factory calibrated Acclima 315Ls performed satisfactorily whether they were inserted vertically or horizontally. The factory calibrated decagons also, they agreed more closely with the neutron probe measurements compared if they were inserted vertically compared with other insertions. And like I said, the watermarks didn't care how they were inserted. So basically, you're going to need field calibration for most of these. If I really wanted to know how much water was in the soil, I really need to calibrate those. If I just want to look for trend lines, well, then I can probably observe those without a field calibration. Okay, and installation matters. Well, we're just now digging them up after 6 years, several years. We're finding some of them had developed shorts over time. Some of them are in pretty good shape. But we're documenting that now. Some references you might want to look at regarding what I've talked about so far: the USDA NRCS Irrigation Water Management Practice Standard, or Standard Practice 449, talks about irrigation water management. Also, NRCS payment schedules. If I want cost share help with soil moisture sensors with telemetry, get $2,100 to $2,900 per unit, or about $6 to $8 per acre. And that was looking at the website just a few days ago. These are updated for location, and they're updated over time, so these can change, but that gives you an idea of cost share help that's available. And certainly talk to your local NRCS office for that. Some other things that we want to look at: irrigation scheduling. When and how much? How much water do we apply? Do we apply pre-season or early season? Looking at timing, irrigation scheduling, and late season irrigation management. These are when a lot of our decisions are made. When I started in this job many years ago, a groundwater district would publish how much water an irrigator would have to apply to fill the soil to field capacity down to 8 feet. Well, now we know if the roots are only going down 3 to 5 feet, there's not much point in irrigating all the way down to 8 feet. So understanding that soil water, also understanding that a lot of irrigation water or rainfall can be lost between pre-watering and planting time. Jim Brodowski did some work years ago where he looked at sprinkler irrigation, low pressure sprinkler irrigation, LIPA irrigation, and subsurface drip irrigation. And 47 to over 50% of the water looking at, he started 5 weeks before planting, and then at planting, he measured how much water was still there. And we'd lost 47% of the water with subsurface drip irrigation and more than half of the water with sprinkler or LIPA. So a lot of water can be lost early season before the crop needs it. So I want to get that water. We're balancing the irrigation capacities. You remember that curve. We're balancing the irrigation capacities with the time we have available and the soil water holding. So that's going to affect our early season and preseason irrigation management. Most of us will have irrigation capacity to meet or exceed early season water requirements, but it's later in the season where I get those, full canopy when I need to really rely on some stored soil moisture. So I want to do that. In-season irrigation scheduling, I can monitor soil moisture. I can look at evapotranspiration estimates like we talked about last week or last time. And, to try to keep up my irrigation scheduled in season. Late season irrigation management, I start looking again at as the crop matures, through the fruiting period, and then I start to dry down or start reducing my irrigation water amounts. I can start letting some of the soil dry down a little bit. I don't have to keep it as moist. So I want to try to take advantage of the knowledge I have of my specific soil characteristics and my specific irrigation system capacities to manage that down, to meet the crop's water needs without over irrigating. Managing the root zone, what I want to do, again, knowing how deep that root zone is, soil sensors can help me understand how deep the water is being pulled, as well as how much water is in the soil. Understanding the soil water holding capacity from that web soil survey or from samples taken from my specific field can help a lot. Again, and then I start looking at different methods for soil moisture monitoring and soil water management, whether I choose a quick and dirty feel and appearance method, or whether I want to take gravimetric samples where I take an undisturbed sample, weigh it, dry it, weigh it again, and the weight lost was the water that was in it, right? And so, or I can use more of these advanced sensors with the telemetry capabilities, and all of them can provide me some useful information. The recommendations, again, understanding crop water requirements, the soil moisture and irrigation system capacities. And again, that's on a case-by-case basis. I don't recommend filling the profile all the way to 8 feet. Some recommended resources I'd like to point you to, again, that USDA NRCS estimating soil moisture by feel and appearance is really handy. It's something that you can take anywhere with a sharpshooter shovel and your hands. You can get some pretty close estimate of how much water's in there, and definitely that's a good way to tell how, if I dig a little deeper, find out where the water is. Another good soil moisture management fact sheet by Dr. Guy Phipps in College Station is available online on his website for now at irrigation.tamu.edu. And it discusses those field dynamics, the soil moisture dynamics in more detail than I've gone into today. And we'll be happy to get a copy for you. Christy and I can get a copy for you if you like. Again, soil moisture sensing systems for improving irrigation scheduling. This paper, Soleil Tagvian, he's no longer at Oklahoma State University. He's at University of Nebraska. Soleil and Jonathan and I put this publication together at the end of that study that I told you about. So we talked about some of our recommendations of sensors and probes and using those sensors for improving irrigation. Another publication, University of Nebraska Lincoln with their NEB guides, they have some really good examples on how to use, for instance, the watermark granular matrix sensors. They have by soil texture, by depth, they really do go into how to interpret the information from these. The granular matrix sensors, a lot of researchers shy away from them, but you saw the curve, they're not as accurate. but they're a lot less expensive, so I can use more of them. And if I'm just looking for irrigation or soil moisture trends rather than the exact amount, they're pretty good. Again, I can hook those up with telemetry systems as well. And it's not a terrible option. It's not as accurate, but I can afford a lot more of them. And so I can get more thorough data from my field. And back to that water holding capacity, the soil effects of soil water holding capacity from the soil health practices. And this actually does summarize a lot of different studies, and it has references or addresses to where you can find a lot more information about that. I will open it for questions. We have plenty of time for that. If anybody wants to correct me or ask, I'll send the hard questions to Christy. So thanks.
Anybody have any questions for Dana? Okay, I do have a question, and it's probably the answer is probably going to be it depends, I can imagine.
Yeah.
But is it better for a producer to water their field quickly with less water, like running the pivot faster, putting out less water, or would it be better for them to slow their pivot down and put more water, but it take longer to get around to the whole field?
That's a very good question, and it depends. You're right. If I have I go back to that permeability. Let me go back some slides. Let me see if I can. I'm going to exit that production. I'm going to be able to go up to the top here. Let's see. All right. Whoops. Am I sharing or not?
No, not yet.
Let me share my screen. Okay. I don't want that. Okay, so whoops, sorry, I'm showing everything here. Okay. I'm looking at this. If I have a more sandy soil, look at the Amarillo sandy soil. That top layer of a sandy soil, it'll take in the water pretty quickly. And so I'm better off irrigating higher rate, trying to get it in, but it's going to be, the water's going to start slowing down when I hit 9 inches or so. So I don't want to have water running off. With a deep soil like a Pullman, I'm better off watering, well, with any of them, with the more finer textured soils like our Pullman clay loam, Olton clay loam, I'm better off watering deeply, less frequently, watering as fast as it will take the water in. I don't want to put on the water so fast that it's running off. So in those fields, I would slow the pivot down, get the water deep, try to get it down 2 or 3 feet deep if I can. So I'll apply an inch or more. I could apply an inch or more if I apply it at a slow enough rate. With a sandy soil like a brownfield, let's see if I got a brownfield somewhere. With a brownfield sand, I've got weird stuff going on here, sorry. Go back to a brownfield sand. With a brownfield sand, it won't hold much water anyway. So I'm going to have to come around a couple of times a week. I'm going to have to irrigate more frequently, especially if I have something like peanuts, because peanuts need the root zone to be moist, but they also need that surface or the pegging and pod development zone moist during that fruiting period. So it depends. That's a long way to say it depends. Sorry.
I think we have to take in consideration of the growth stage as well as the type of
Yeah.
soil. And that'll help us make a better management decision at that point.
Absolutely. And
Okay.
later in the when I'm looking at full canopy, if I'm only applying a half an inch of water a day and the crop is using a half an inch of water a day, I'm having a hard time gaining ground or keeping up with my irrigation. So you make a very good point there. Thank you. Another thing I probably skimmed over too closely was this figure on this one. Infiltration rate, something that I've done a lot of soil physics work, and that KSAT, or that's the maximum that's the saturated hydraulic conductivity. If I have, especially, it's more evident in a shrinking swelling clay where I start out with a dry soil, it'll take in water really fast. But then as those clays start to swell up, the infiltration capacity, the permeability declines to that reassume a steady state of about a saturated hydraulic conductivity. That value is important in, for instance, septic tank design and the drain fields. How fast can that soil take in water? If I apply water faster, then I'm going to have ponding problems, runoff problems. If I can see that sometimes with subsurface drip irrigation, where I see water start to come up the top. I'm exceeding that, the water's ability to hold. I'm exceeding the soil's ability to hold the water and the soil's ability to take in the water, the infiltration rate. That can also happen when I have a hole in my tape and and the water comes up to the top in only one place. So that's another way to find it. Any soil specific questions?
Looks like we might have a question in the chat here in just a second.
Okay, sorry, I can't see it.
Someone is typing.
They're saying you're wrong. If you're interested in the polyacrylamides or the PAM applications, that's used a lot. It's used more in surface irrigation, furrow irrigation, and the USDA ARS lab out of Kimberly, Idaho has done a lot of work on that. So if you want to dig more into that, the Kimberly, Idaho lab has some really good links and research there.
Okay, we have a question in the chat.
All right.
In fields with multiple soil types, it would be best to have several monitors, but maybe not feasible. Is it better to put monitors in heavier soils or sandier soils for an average?
Oh, that's a good one too. That's a good question too.
That's a great question.
That's a very good question. And it's easy when I have just one or two soils, obviously. Um, I've seen some fields up in Lipscomb County that could have a dozen soils. It's insane. Really, you want to look at your most limiting soil. If I just have a lot of times if I have multiple soil types, it may be a Olton and Pullman, and their characteristics are not that much different. Same way goes with an A-cuff and an Amarillo. They're not hugely different. We have done some work on optimizing how many sensors we need to balance that. Again, that's where some of the less expensive sensors with telemetry can help, because I can put a lot more in the field. This one, for instance, this example, I would put it in the this larger unit. I would find that soil. It's about Montel clay. That would be this is down around Uvalde. The UVA and the Montel clay A and B are really not that much different. It's the slope that's different. The water holding's not that much different. But again, if I had a big change in soil texture, I would want multiple sensors, unless it's just a small part of the field. Then I probably wouldn't bother. In reality, in research, I would, but in the real world, I probably wouldn't. As a researcher, I say more sensors are better, but I know that they cost money too. None of the sensors are easy to install, right, Christy?
Right. I was going to echo that. Installation is extremely important with those sensors
Yeah.
because an installation that gets you an air pocket can definitely provide you with some interesting data
Yes.
comes across.
Yeah.
So
It's just
definitely
wrong.
install it correctly, or find somebody who is experienced in that to install it.
Yeah, if they've got the right tools. Another thing too, some installers will put in a slurry to help improve the contact. So they might drill a hole that's bigger than the diameter of their sensor, insert the sensor, and then backfill with a slurry. So it's technically the kind of same, it's the same soil, but it's going to be a totally different texture or structure around it. And so sometimes those numbers, if my sensor is only measuring a short distance diameter, those numbers are changed by the slurry. They're by that interrupted structure, that interrupted um, bulk density surrounding it. So the numbers are going to be probably different from the soil surrounding it. Another question is, do I put it in the field row or in the furrow or what? Well, I want to know where the roots are. If I have an alternate furrow situation, I don't want to install my sensor in a trafficked furrow. I don't want to be driving over them. So if I have it in the row with the plant, that's a good place to have a sensor. If I have a non-traffic furrow in between two rows, I can figure out if if my irrigation is migrating, how far it's going across. If it's just if my roots and my moisture are just under the plant row versus is that water moving across laterally? Again, it's tough. I don't want to be driving tractors over my sensors too much or at all. Um, Telemetry's made it easier where I don't have to have as many dadgum wires. So that makes things a lot better too. Um, as far as subscriptions go, I can have multiple telemetry systems connect to a low-raw gateway, and then I have just one subscription where the data are communicated from different nodes to a central gateway system, and I can save some money on data subscriptions that way. Other questions? I think I put them to sleep, Christy.
I think it's a lot of great information. It takes a little bit to digest. I understand that. So I definitely think that if you have further questions, if you think of a question, maybe like during the week or something that you need to ask, send me an email. We'll get that question answered.
Yes.
Hopefully you are all receiving my emails. You have made it online to this webinar series. And so hopefully you are receiving my emails. If you have any questions, again, please feel free to send those to us. We would love to answer any kind of questions that you have so that you are getting the learning experience that you are expected.
Thank you, Christy. And thanks everyone for your time and attention. And we look forward to your questions. Also, again, those links are in the presentation to those additional information resources, and we can send those links out to you as well.
Yes, I'll send those out in the follow-up, hopefully this afternoon.
Thanks, y'all.
Thank you.